Here we go with an AP style problem. So we have a force holding a block on an incline as shown, and we have some coefficient of static friction between the block and the incline of mu, and we want to know how much force we need to push down with here to keep this block at rest. So what I'm going to do is I'm actually going to redraw this down here and set up my forces acting on the object. So I have the force of gravity going down. I have my normal force going up like that. I have that pushing force is going down at an angle like that, perpendicular to my incline, and then I'm going to have the force of friction going up the incline, keeping this at rest. Just like I always do, I'm going to tilt my axis here, so I'm going to have my x-axis parallel to the incline, y-axis perpendicular to it, and that means that gravity is going to have components. So my x component is going to be Fg sine of theta. My y component is going to be Fg cosine of theta, like it always is. So once I have that, I can go ahead and set up my F equals ma in both the x and the y direction. I'll start with the y here. So I have Fn is going up minus F, that downward pushing force, minus Fg cosine of theta, the y component of gravity, and that's going to be equal to 0 because we're not accelerating perpendicular to our incline. So I'm going to go ahead and solve for my normal force. My normal force is going to be equal to F plus Fg cosine theta, but I'm going to substitute in mg cosine of theta. In my x direction, I'm going to go ahead and set up my forces as well. So in that direction, I have the force of friction going up the incline, so I'll make that positive, although you could make it negative, minus Fg sine of theta going down the incline, and that's going to be equal to 0 because the object is remaining at rest. Two things I'm going to do here. Number one, because we're dealing with the minimum amount of force needed to keep the object at rest, even though we're dealing with static friction, rather than saying static friction is less than or equal to mu times the normal force, I'm just going to say it's equal to, because we have that piece of information that lets us know that our force of friction will be at a maximum. So I can make that substitution there. And I'm also going to substitute in mg for my force of gravity. And so those two are still equal to 0. So I'm going to plug in that expression I just had for my normal force, so mu times F plus mg cosine of theta minus mg sine of theta is equal to 0. This is what I ultimately want to solve for, so we're just going to do a little bit of algebra and rearranging here to get that. So first I'm going to distribute that coefficient of friction, so mu times F plus mu times mg cosine of theta minus mg sine of theta equals 0. I'm going to move this term and this term over to the other side. So I get mu times F is equal to mg sine of theta minus mu s mg cosine of theta, and then I'm just going to divide by mu, and I end up getting here that the force is going to be equal to mg sine of theta minus mu mg cosine of theta all over mu. I was writing mu s there for this coefficient of static friction, but we see that that's just given as mu without that subscript, so I just dropped it. And so that is going to be answer D there. Now they did rearrange it slightly to factor out the mg in each term, and so what that looks like is that force is just mg times sine of theta minus mu cosine of theta all over the quantity mu. But same expression in those two final answers, but the answer there is going to be D. For the next one here, we have 3 position versus time graphs for different objects shown, and we want to know in which situations is the sum of the forces on the object 0. So what that means is when the sum of the forces is 0, that means that my acceleration is 0. That's the key. So looking at these graphs, I want to look for situations where my acceleration is 0. Going back to position graphs, we know that on a position graph, acceleration is represented by a curve. So I want to look for graphs where I have a curve. So for the first graph, no curve, no acceleration. For the second graph, no curve, no acceleration. For the third graph, it's concave up, so that's a positive acceleration. So in which cases do we have zero net force? That would be the two with zero acceleration, 1 and 2, so it's answer C. Moving on to this next one, we have a block being pulled across the surface with some force F up at an angle as shown. And we also have a frictional force that's down here, okay, with the magnitude of little f, and we want to find the acceleration of the block. So the first thing I'm going to do is think about all the forces acting on this object. So we have our normal force. We have this F, which is going up at an angle. Here they're using the Greek letter phi instead of theta, but same difference. We have the force of gravity going down, and we have this frictional force, little f, going back. Okay, in this case, that's not the coefficient, that is the force. What we're always going to do here is break that f into its components. So f cosine of phi and f sine of phi. We want to find the acceleration, which is going to be in the x direction. So I'm actually just going to set up my max here. Okay, I don't have a coefficient of friction, so even though a lot of these friction problems require us to set up may to get the normal force, here we don't have to because we don't actually need to worry about the coefficient of friction in this particular problem. So in the x direction, I just have f cosine theta minus little f, that force of friction. That's equal to m times my x acceleration. So if I solve for that acceleration, it's going to be f cosine of phi minus little f all over m. And that's going to be equal to my acceleration. And so we get an answer there of D. Alright, moving on to my next one, which is a free response problem here. So we have two spheres, A and B, that are made of the same material and have the same radius, but one is solid and therefore is twice the mass. So sphere A is the solid one, is twice the mass of sphere B, which is hollow. Draw from the same height, both in a vacuum and air. So air resistance is negligible in the vacuum, but when in air there's a non-negligible drag force, meaning we have to account for it, exerted on each sphere. And we are given this hint that for simplicity we're going to assume that drag force is the same for both spheres. All right. So first thing we want to do here is we want to draw the free body diagram showing the forces on each sphere both in the vacuum and in air. So in the vacuum, we just have the force of gravity. It does say draw all these forces with the correct relative length to reflect the magnitude. So since A has twice as much mass as B, that means that the force of gravity acting on A is going to be bigger than the force of gravity acting on B. So I'll call them FGA and FGB. In the air, same two forces, force of gravity acting on both, FGA and FGB. We notice that the length of the vector hasn't changed because the force of gravity has not changed. In air, though, we have a drag force, which I'll call FD, acting on each object in the opposite direction. Okay, so that's what those forces will look like. I do notice that my drag force is smaller than both of the forces of gravity. If that were not the case, the spheres wouldn't move at all. Alright, so for the second part, we're asked to respond to the question, when dropped in a vacuum, which one hits first? And when dropped in air, which one hits first? And we're asked to answer in a clear, coherent, paragraph-length response. So when we're doing these, we want to start with our answer. So let's start with the vacuum. When dropped in a vacuum, which sphere hits the ground first? So I would say in a vacuum, they hit the ground at the same time. There's my statement, very clear, and it answers question 1 here. And now I'm going to have to back it with some evidence. So the first point I would make is that sphere A, since it has twice as much mass, has twice the force of gravity as sphere B. So that statement alone would make it seem like sphere A would actually accelerate faster, but the important point here is that sphere A does have twice the mass, and therefore it needs twice as much force in order to accelerate, which is what Newton's second law tells us. It's really shown by Newton's second law, which tells us that the force is directly proportional to the mass for a constant acceleration. So there we have a nice explanation for our first part. We've started with our statement. We've led through a few basic concepts to get to really the key, and that is Newton's second law. Force, or object A, has twice as much force acting on it, but because it also has twice as much mass, and force is directly proportional to mass times acceleration, it needs twice as much force in order to accelerate at the same rate. Okay, so there's the answer to the first part. Let's think now about part 2. So in air, for the second part, sphere A is going to hit the ground first. There's our statement once again. We now want to back it with a reason, and there's a few avenues you could probably take here, but I would say that both objects have the same drag force acting on them, but B has less mass, and that means that that same drag force affects object B more. Once again, I would cite Newton's second law, except this time I would say that for a given force, mass and acceleration are inversely proportional. So that means that the less massive object will experience the greater change in acceleration for the same force. You also, I think, could argue part 2 by talking about how the drag force is going to represent a bigger percentage of the force of gravity acting on object B than it is on object A, simply because drag force is the same in both cases, but object B has a smaller force of gravity. So I think that's another route you could take. I would ultimately, though, link it to Newton's second law. We always want to make sure that we're linking our reasoning for these paragraph length response ones to some physics concept. All right, and in this case, Newton's second law is the one that really pertains the most. All right, for this next one, we're going to do an experimental design one, and we want to be able to determine the coefficient of static friction between a long, flat wooden board and a small wooden block. All right, and so in the first part, we're going to draw a diagram of our setup and talk about the measurements we make, and in the second part, we're going to describe the overall procedure. So let's start with the diagram. So I'm going to start here with that block sitting on the board, and I'm going to keep in mind that when determining the coefficient of static friction, we have that equation that the force of friction is less than or equal to mu times the normal force. So basically, in order to solve this, I need to somehow determine the force of friction and the normal force. And what I would think about is when friction is at a maximum, when static friction is at a maximum, our force of friction is going to be equal to mu times my normal force. Okay, so I'm going to be thinking, and again, I'm kind of thinking about the whole experiment here to be able to answer this, and sometimes you'll need to do that for these ones. But what I'm going to do is I'm going to force this to be a situation where static friction is at a maximum. And the way I'm going to do that is I'm going to be looking at that point where it begins to slip. Sometimes we talk about that verge of slipping. And so that's the situation I'm going to look at, is that minimum force needed to make this object begin to move. In terms of measurement, what I would do is I would attach a force probe to my block here. We don't necessarily need to mention that it's hooked up to the LabQuest, but that's kind of an assumed thing. But the force probe part is important. So we're going to connect a force probe, and that's going to be used to measure the pulling force. And I would also have a scale, and that doesn't necessarily need to be with our setup, but a scale off to the side. And so we're going to say we use the force probe to measure the pulling force, and we're going to use the scale to get the mass of the block. So we've now completed part 1, talking about the raw data we're going to get. And again, I know we're doing this in the order the questions are asked, but it might actually be easier to do part B first and then go back and think about how you're going to get the information that you need. So going on to part 2, describe the overall procedure that would be used, including any steps necessary to reduce experimental uncertainty. So since we're focusing on that verge of slipping, what I would say is pull horizontally, and that's a key point, on the block with the force probe. And what we're going to want to do is slowly increase the force until the block begins to move. What we're going to want to do is we're going to want to record that maximum force when the block begins to move, because at that point, that pulling force is going to be equal to the maximum force of friction. The other thing we want to do is we want to get the mass of the block using our scale. So there we have our basic procedure. In order to reduce experimental uncertainty, I would say repeat this experiment using putting masses on top of the block so we get a variation in the mass of the block. So there's our setup for part A. In part B, we want to derive an equation for the coefficient of static friction in terms of the quantities measured from part A. So we're going to go ahead and set up part B here to derive that expression. I would start, of course, with our free body diagram. So we have the normal force, we have the force of gravity, we have our pulling force, and we have the force of friction. So in order to get the coefficient of static friction, we're going to say in the y direction, the normal force minus the force of gravity equals 0. And so our normal force then is simply mg. Okay? And in the x direction, we're going to have the pulling force minus the force of friction, and that's going to be equal to 0. Also, because we're thinking about that point when the block just begins to move, that minimum force necessary to make it start to move. So in that case, on the verge of slipping, our acceleration is 0. So our pulling force is equal to the force of friction, which is mu s times our normal force. Okay, here force of friction is at a maximum, so that equation, we already talked about that before, how we can take that equation and just set it equal. FF is equal to mu times the normal force here because friction is at a maximum. Substituting in from the first part, our pulling force is equal to mu s times mg. So that means that our coefficient of friction here is going to be our pulling force divided by mg. And so this pulling force is measured with the force probe that we mentioned before, and our mass is measured with the scale. G obviously is a known quantity, but this would allow us to get our coefficient of friction in terms of the variables we described in part A. If you did want to get fancy, and this certainly is not necessary, but we could say that we could also graph FP versus mg, and then our slope would be mu s. So that also would be a valid way of doing it, is creating that graph of FP versus mg, and then our slope is equal to our coefficient of friction. Not necessary, but it is possible. The other option here, and I'll just discuss this real quick, is we could put our box on an incline and slowly increase that angle until it starts to slip. Same basic idea. It would just change our free body diagram, and we actually don't need any force probe there. It's just something to measure that angle. But that's another option. We're still getting at that idea of we want to look at the situation where the block's about to begin to move, whether it's from the force pulling it or from the angle being steep enough that it starts to slide. Moving on to part C, so we have some data here from 6 different lab groups, and what they actually did was they tested both the coefficient of kinetic and the coefficient of static friction, and we have this nice data table here showing their results. And the first question is, based off of these results, can we conclude that static friction and kinetic friction are the same? So we take a look here at the average, and we see that those average values are the same for both static and kinetic. However, if we look at the data a little bit closer, we take a look here at group number 5, and we see a pretty big discrepancy, right? If you look at our coefficients of kinetic friction, they're all in that 0.4 range except for group 5, which has 0.74. And if you look at the static frictions, they're all in that 0.5 range except for group 5, which has 0.23. So that right there is indicative of an outlier, and that's really what is skewing the data. So the answer here, the box we would check, is not equal. And our reasoning is group 5's data represents an outlier. I would say all of the kinetic coefficients are around 0.45, while all the statics are around 0.55 for the other groups. And then I would finish by saying the only reason the averages are the same is because group 5 has data that is an outlier. So there's our answer to part C. One last part here, part D. Last question here, part D, is asking about what would happen if we glued a metal disc to the top of the block, which would increase the mass of the block disc system. What would happen to the coefficient of friction? Coefficient of friction would remain the same in this case because the coefficient of friction depends on the two surfaces, and those have not changed. Although the force of friction would increase, the coefficient depends only on the surfaces, so it would stay the same. Alright, one more AP style problem here. So we have a child on a sled traveling at a speed of v at the bottom of a hill. The child slides up the hill, which is sloped at an angle of theta, and reaches the top of the hill, comes momentarily to a stop, and slide back down. And so first we want to draw the forces acting on the child in both situations, both sliding up the hill and sliding down the hill. So in both cases, we're going to have the force of gravity, of course. We're going to have our normal force, okay? And we're going to have a force of friction. Here's the key difference, though, is when we're going up the hill, we're traveling that way. And so that means that my force of friction is going down the hill. So this is the up case. And when we're going down the hill, all right, my force of friction is traveling up the hill, opposite the direction I'm moving. I'm not going to go ahead and break these into components because it does say draw the forces, not components, but I will do that eventually when I get to later parts of this problem. For part B, when the child returns to the bottom of the hill, will they be traveling with a speed greater than, less than, or equal to v? So I'm going to look at my forces here, and I am going to think kind of off to the side about those components of gravity. So we're going to have the Fg sine of theta and Fg cosine of theta, and that's going to be true for both objects when we break that force of gravity into x and y components. And here's what I would think about and what I would look at is when I'm going up the hill, Fg sine theta and Ff are both working with each other, all right, to slow the object down and ultimately lead to an acceleration that is down the hill. However, when I go down the hill, all right, that force of friction and the Fg sine of theta are working against each other. And so even though I'm accelerating down the hill, it's going to be with a lesser acceleration. So what does all that mean? That means that I'm not going to accelerate as much, and so it's not going to be a completely symmetrical situation. I'm going to be going slower when I get to the bottom of the hill than I was initially. And what I would say is going up, the force of friction and the x component of gravity are in the same direction, but going down, they are in opposite directions. And that means the acceleration is greater while going up and slowing down than it was while going down the incline and speeding up. And that ultimately means the velocity is less when we return back to the bottom of the hill. Alright, so there we have our answer to B. This is one of those ones where doing C and D might actually help you answer B. As we're going to see, we're going to derive an expression for the acceleration in both cases. So if that does help you out, feel free to do those second parts before you do part B. So I'm going to get some space here to work on part C. And in part C, we want to find an expression for the acceleration while going up the hill. So I'm going to think about my forces while going up and set up my max and may, of course. So in the y direction, we're going to have Fn minus Fg cosine of theta equals 0. So that means that my normal force is equal to mg cosine of theta. We know we're not accelerating perpendicular to the incline, so that's what my normal force is. In the x direction, we are accelerating, so I'm going to have negative ff minus fg sine of theta, that x component of gravity, equals m times ax. I'm going to make some substitutions, so negative mu times Fn is my force of friction, because I know my coefficient of friction is just mu. I'm going to substitute in for f of g, make it mg sine of theta, and that's equal to m times my x acceleration. Two last steps here. I'm going to substitute in for Fn. I'm going to make it mg cosine theta minus mg sine of theta. And I'm going to divide everything by the mass. And so that mass will cancel out on the top there. And we're left with an acceleration here that's just negative g sine of theta minus mu g cosine theta. So there I have my answer to part C, the acceleration while I'm on my way up. Moving on to part D, my acceleration on the way down. I notice that nothing really changes in the y direction, so I'm going to say that Fn is still equal to mg cosine of theta, because there haven't been any new forces. There's nothing really different about it in the y direction. In the x direction, however, we will have some changes, so I'm going to set up my max once again, and that's going to now be fg sine of theta. I'm going to make that positive because it's in the direction of our acceleration, minus ff. And it doesn't matter which one you make positive, but they should have opposite signs. And that's going to be equal to m times my x acceleration. Substituting in for fg, I get mg sine of theta minus, for my force of friction, it's going to be mu mg cosine of theta, and that just comes from mu times the normal force. I am taking a little bit of a shortcut there. That equals max. My masses divide out here, and so in the x direction here I get an acceleration of g sine theta minus mu g cosine theta. And that supports what we said here in part B. I can clearly see that my acceleration here is going to be bigger than my acceleration here, because in this case, both of those terms, g sine theta and mu g cosine theta, are acting together. They have the same sign, and so that's going to add up to a bigger value, or a bigger magnitude, than this acceleration here on the way back down. So for my last step, I need to draw the velocity versus time, position versus time graphs for this child on the sled. So for the position versus time, I'm going to start at the origin, which you don't necessarily have to do, but that's what I'm going to do. And I'm going to just say the child's traveling in the positive direction, okay? And again, as long as we're consistent, that's okay. So I'm going to first show the child slowing down to a stop on the way up, okay? And then speeding back up on the way down, but it's going to be a little bit more gradual. We do, though, get back to the same point, because we reach the bottom of the hill. We reach that same position. On the velocity versus time graph, we are going to start with some positive velocity. We're going to slow down to a stop on the way up, and then we're going to speed back up on the way down, but we clearly see a lower slope here, indicating the smaller acceleration that we have on the way back down than on the way up.